Welcome to today's presentation on CTIPS 005, Data-Driven Inspection Planning for Utah Culverts using Federated Learning. This presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University. We are a dynamic partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, along with the Center for Transformative Infrastructure Preservation and Sustainability, also known as CTIPS. Through these partnerships, TLN delivers tech transfer, best practices, training, and research to the transportation industry. For more information, visit our website at translearning.org. The research materials can be accessed through the CTIPS website. I will place that link in the chat once I'm done here. A recording of today's session will also be available both on the YouTube channel and the CTIPS website after the session concludes. Please give us a couple days to get it processed and posted. To help maintain a smooth experience for all participants, please set your status to Do Not Disturb and ensure your microphone is muted when not speaking. If you decide to take a call, please make sure you are muted before you answer that call. Feel free to ask questions or request clarification at any time throughout the presentation. We will address them as they come in. And then, of course, there'll be an opportunity for some questions at the very, very end. Joining us today, we have Dr. Abbas Rashidi. He is a PhD in CPC, is an associate professor of construction engineering at the University of Utah. And joining him today is Poria Mohammed. He is going to be giving your presentation today, and I will go ahead and turn it over to you to introduce yourself.
Hello, everyone, and good afternoon. My name is Poria Mohammedi. I'm a PhD candidate at the University of Utah. My focus is on data-driven application on infrastructure asset management. And today I want to present our CTIPS research project. The project title is Data-Driven Inspection Planning for Utah Culverts using Federated Learning. This work was conducted at the University of Utah with Dr. Rashidi as the principal investigator of the project. The main goal of this project is to explore how artificial intelligence and federated learning can support more efficient and privacy-preserving inspection planning for culvert infrastructure. Let's first explain why culverts are important and why their condition matters for transportation safety. Culverts are pipes or tunnel-like structures that allow water to pass safely under roads, railways, and embankments. Although they are often hidden below the roadway, they play a very important role in protecting transportation infrastructure. When culverts function properly, they help manage stormwater, prevent flooding, and protect the road structure above them. However, when culverts deteriorate or fail, the consequences can be serious. A failing culvert can cause road collapse, flooding, emergency closures, and safety hazards for drivers. The image shown in this slide is an example of when culverts do not function properly, which caused Payson Canyon Road to be completely washed away in Utah in 2023. This is why culvert inspection and maintenance are so important. Agencies need to know which culverts are in good condition, which ones are deteriorating, and which ones should be prioritized for repair or replacement before a failure occurs. Now that we have understanding why culverts matter, the next question is, what specific challenge does Utah face when trying to manage and inspect its culvert inventory? The challenge becomes clearer when we look at the scale of Utah's culvert network. Utah has more than 47,000 culverts distributed across UDOT highway system. Inspection and monitoring every culvert on a frequent cycle is slow, labor-intensive, and difficult under limited inspection resources and budgets. Because of this, UDOT needs a more efficient way to decide where inspection efforts should be focused on. The current approach is a reactive maintenance, which means repairs only happen after failures occurs, and this causes lots of negative consequences for UDOT. This project is motivated by the shift from reactive maintenance to proactive maintenance. Instead of waiting until a culvert fails, the goal is to predict which culverts are more likely to need attention. And to do that, machine learning can support us by learning relationships between culvert characteristics and features and observed condition ratings in the plans. So our research team at the University of Utah proposed using AI and machine learning to predict the condition of culverts and prioritize the inspections for critical culverts. As a result, avoid the consequences of culvert failure for UDOT and also the travelers of highway systems. This slide shows the basic idea of how machine learning model works. During training, the model uses historical culvert records where both features and condition ratings are known. These features may include physical attributes, environmental attributes, and other variables related to deterioration of culverts. The model then learns patterns that connect those features to condition ratings. During deployment, we provide the trained model with information about a culvert that has not been recently inspected, and then the model predicts its likely condition in the future. The value of this approach is not to replace inspection, but to make inspection planning more strategic. If the model can identify high-risk culverts, agencies can focus on field inspection where they are most needed. For predicting the culvert conditions, we had to consider that different culverts may deteriorate differently depending on their attributes such as material, age, size, length of culvert, environmental conditions around the culvert, and traffic exposure. So a data-driven approach can be very useful, but only if we have enough high-quality data to train the machine learning model with them. But the main challenge is that Utah's available culvert inspection dataset is only 272 culvert records, which is relatively small compared with the size of the actual culvert inventory. The actual culvert inventory for Utah is more than 47,000. This creates a data limitation problem for machine learning. In other words, if we only train a prediction model using that limited local dataset of UDOTs, the model may not learn enough patterns to make accurate and generalizable predictions for other culverts that have not been seen in the dataset. To avoid the risk of using a limited dataset, two common solutions are used in similar studies in the past. One is data augmentation techniques, which means adding synthetic data to the limited dataset and balance it with the advanced analytical techniques that we have in data science. The other one is collaborating across multiple state DOTs. Many DOTs maintain culvert inventories and inspection records, and combining those data sets could provide a much richer training set. A larger and more diverse dataset would help the model learn patterns across different materials, climates, roadway settings, and inspection histories. But this solution introduced another major challenge. This challenge is data sharing. Traditional centralized machine learning assumes that all raw data are gathered into a single location before training. That approach can improve model performance, but it creates several roadblocks for DoT collaboration. First, agency may have privacy, policy, or legal concerns about sharing raw infrastructure records. Second one is different DOTs may use different data formats, different inspection procedures, and different rating systems. And the third one is even when agencies are willing to collaborate, transfer the centralized raw data, it can be time consuming and difficult to manage in terms of security risk of data sharing. These challenges are not only technical, they are organizational as well. Therefore, we need a modeling approach that supports collaboration while allowing each agency to maintain control over its own local data. So the key question becomes, how can multiple transportation agencies benefit from each other's data without requiring each agency to share its raw data? This challenge can be addressed with federated learning. Federated learning is a machine learning paradigm that allows multiple organizations or agencies to train a shared model collaboratively without directly sharing their raw data. In our case, each state DOT can keep its culvert data locally instead of sending raw inspection records to a central location. This makes federated learning specifically useful for transportation agencies because it supports collaboration while preserving agency control over local data. It allows agency to learn from a broader multi-state dataset, but without the risks and barriers associated with centralizing all raw records. To make this idea clearer, let me walk you through the federated learning process works step by step. In federated learning, first we create a unified format for our data feature. So each agency's data is mapped into a unified feature format. Next, a global model is initialized and distributed to each agency. Each agency trains that model locally using only its own culvert records. After local training, the agency sends model updates back to the federated server, not the raw datasets, only the model updates. The server aggregates the model updates typically by averaging them to create a stronger global model. That improved model that improves the global model architecture. Then the architecture is sent back to the agencies for another round of local training. This process repeats until the model converges. The important point is that the data stay local throughout the training process, but the model updates will be shared between the agencies. Based on the motivation that I explained in few slides before, our study had three main objectives. The first objective was to test whether federated learning is feasible for culvert condition prediction when local data is limited in DOT. This is important because Utah's local dataset alone may not be large enough to support a highly reliable machine learning model. The second objective was to compare federated learning with traditional centralized machine learning approaches. We wanted to understand how close federated learning can get to a centralized model where all data is combined into one dataset. The third objective was to quantify the privacy benefit of federated learning. In other words, we wanted to evaluate whether we can still achieve strong predictive performance without requiring states to transfer raw culvert records. Together, these objectives allowed us to evaluate federated learning from both a technical and practical transportation agency perspective. To achieve these objectives, the first major step is to build a consistent data foundation across the participating states. To do that, we had to collect culvert data first. We collected a total of 8,240 culvert data points from 6 states in the United States. The states are Colorado, Vermont, Ohio, Massachusetts, New York, and Utah. These data sets provided a broader training environment than Utah's local data alone. However, multi-state data also introduces inconsistency. Different states may use different inspection variables, different rating systems, and different formats and different coding conventions. Before modeling, we need to make the dataset comparable. This data preparation stage was essential because machine learning models are highly dependent on the quality and consistency of input data. If the data are not standardized, the model may learn misleading patterns or fail to generalize across states. To address this issue, we developed a pre-processing pipeline. The goal was to standardize physical features, environmental features, and condition ratings into a unified format. In particular, we mapped the condition information of UDOT's 5-point rating system so that all records could be interpreted consistently. This step is extremely important because machine learning models depend heavily on the quality and consistency of the input data. Without the standardization, the model might be confused and not learn the pattern for predicting culvert conditions. This step allowed us to compare centralized learning and federated learning under common features and label structure. The pre-processing pipeline was therefore not just a cleaning step, it was a necessary foundation for any cross-asset learning framework. Because the dataset were different, we selected a common set of features that could be standardized across states. These include physical features such as material, shape, length, and age, as well as environmental features around the culvert, such as soil properties and flooding frequency in the location of culverts. The target variable was the culvert condition rating, which is the model learned to predict from these features. The physical features were included in the DOT inventories, and the environmental features were obtained from Web Soil Survey website manually. We had to put lots of time for collecting those collection data manual data collection, and this we use help from our bachelor students in our team. After creating this standardized data foundation, we developed and compared several machine learning models. There are four models that we developed in our study. The first model was Utah CL, which is a baseline centralized model trained only on Utah's small local dataset. This represents what happens when Utah relies only on its own limited label records. The second model, which was Utah Smooth, used Utah data with synthetic samples generated through a smooth technique to address class imbalance in the Utah's dataset. The third model was AllCL, which is the centralized benchmark model, and used all 6 states raw data, which merge into one dataset. This gives strong performance but requires raw data sharing. The fourth model, AllFL, is our proposed federated learning model across 6 states. It used collaboration across agencies, but raw data were never shared between these agencies. For the core prediction model, we use an artificial neural network. Artificial neural network can learn by adjusting internal weights between hidden layers so that the difference between predicted condition classes and actual labels becomes smaller during training. In our implementation, the model used a ReLU activation function and a cross entropy loss function, which are common choices for classification tasks. The same neural network architecture was used across modeling scenarios, the four modeling scenarios, to keep the comparison fair. This allowed us to focus on the effect of the training strategy: local undertraining, synthetic augmentation, centralized multi-state training, or federated multi-state training. To address UDOT's limited data set, we use data augmentation, as we mentioned in the past. There was a class imbalance in UDOT's data set. In culvert data set, poor condition or critical conditions culverts are often much less frequent than fair or good condition. The standard machine learning models can become biased toward the majority classes because those examples dominate the training data. Smooth is one common method to address this problem by generating synthetic examples for minority classes. We included Utah Smooth to test whether synthetic augmentation could compensate for UDOT's limited data or not. However, synthetic data are not the same as real examples from diverse field conditions. This comparison helps us understand whether federated learning provides a better way to improve minority class learning or not. For the federated learning implementation, we use Flower, an open source framework for simulating and developing federated learning systems. We applied horizontal federated learning to tabular culvert dataset that we collected from DOTs and completed by adding the manual data collection. Horizontal federated learning is appropriate here because agency has similar culvert features, but the culvert records belong to each agency are different. So the target variable is same, but the features also same, but the number of records are different. The aggregation technique that we used here was federated averaging, which means we only average between the model updates that have been sent to this server. It can be changed in the future studies. In each training round, the local models were trained at each participating state, and the server combined those updates into a global model. The core machine learning model inside the federated framework was artificial neural network. This setup allowed us to simulate how multiple state DOTs could collaborate without transferring raw data between each other. The performance results show the central finding of the project. The federated model, ALFL, captured about 96% of the raw performance of the fully centralized model, while avoiding centralization of raw data. This is important because the centralized model represents a best case benchmark where all state data are merged, but that approach may not be realistic for many agencies. The federated model also clearly outperformed the Utah-only and synthetic data approaches. So the result is not simply that federated learning protects data, it also provides meaningful predictive value by allowing the model to learn from authentic multi-state patterns. Looking at the results more specifically, the ALFL model achieved 80.4% accuracy, which is close to centralized ALCL model at 84.1%. This small gap is important because the centralized model requires raw data sharing, while the federated model does not. Uh, Federated learning also outperformed the Utah-only and Utah-Smooth models across the evaluation metrics. Another important result is the improvement in the minority class. In infrastructure asset management, the poor condition is very important. Here you can see the confusion matrices of these models, and detecting critical defects is very important in culvert management. So missing a class 1 culvert can be very costly because those are the cases associated with severe deterioration and potential failure. The Utah-only centralized model failed to identify any class 1 critical culverts, meaning it was effectively blind to the most urgent cases that we wanted to find out. In contrast, the ALFL model successfully identified 80.7% of class 1 critical culverts. This is a major improvement where it matters most. For inspecting, planning, and maintaining the culverts, this federated learning can help agency better and much more valuable. A natural question is why not simply use data augmentation such as a SMOT on our limited data set? The results show that synthetic augmentation has limitations. A SMOT can help balance the dataset mathematically, but it does not create new real-world deterioration patterns. It generates synthetic points based on existing Utah records, which means it can duplicate or amplify local limitations. In our results, SMOT introduced severe prediction errors in some majority classes. Federated learning provides a stronger alternative because it brings in authentic variation from other states while still keeping raw records local and safe. So the benefit comes from real diversity in the training signal, not just synthetic balance. Here we can take a look at AI collaboration metrics. Traditional Utah-only modeling protects local data, but it is limited because the model only learns from a small data set. On the other hand, a fully centralized model can improve performance by using all available data, but it requires agency to share raw records. Federated learning provides a middle ground. It allows agency to collaborate and train a stronger shared model while each agency keeps its raw data under local control. This is the main value of the federated learning framework. It does not force agencies to choose between privacy and performance. Instead, it creates a pathway where agency can improve prediction quality while maintaining control over their data. Behind the technical result, it is important to understand what this means in practice for transportation agencies. The practical value of this work is that it can support better inspection, planning, and asset management instead of treating all culverts the same. Agency can use predicted condition data to prioritize inspections of assets more likely to be in poor condition. This can help inspections of assets more likely to this can help inspection of assets that could be failed soon. Also, it can allocate limited inspection resources more effectively, reduce the chance of unexpected failures, and support more proactive maintenance decisions. The approach is also scalable because it can be extended as more agencies participate. Importantly, the framework supports collaboration without requiring agencies to give up control of their raw infrastructure data, which makes it more realistic for transportation practices. In long term, this project shows how transportation agency can collaborate through AI without giving up ownership or control of their data. Federated learning could support a broader national learning network where each DOT benefits from the collective experience of others while maintaining local data governance. This is specifically valuable for infrastructure asset management, where failures are rare but high consequences. As more agencies participate, the shared model can become more generalizable across different climates, different materials, and different inspection practices. Also, roadway environmental will be added to these generalizable model. The long-term impact is a more proactive, data-driven, and collaborative approach to infrastructure preservation. Of course, this work has also limitations, and those limitations help define the next steps for future research. First, federated learning still requires some level of feature standardization. In this project, only features that could be standardized across states were included, which means some potentially useful variables had to be excluded. Second, class imbalance remains a challenge. Poor condition culverts are usually less common, but they are very important for inspection planning. Future work should continue improving prediction for these underrepresented classes. Third, we use a basic federated learning framework, but more advanced algorithms such as FedProx or other personalized federated learning methods may further improve performance and reduce the gap between federated and centralized models. Fourth, this study included 6 states. Expanding the framework to include more DOTs could improve model generalizability and create a stronger national scale learning network. Looking forward, future research can explore federated transfer learning to handle non-uniform feature sets, apply the framework to other infrastructure assets, and develop a real-time federated learning pipelines that updates as new inspections are collected. To conclude, this project demonstrated that federated learning is a feasible and promising approach for culvert condition prediction and inspection planning. The proposed all-FL model achieved strong performance while avoiding direct raw data sharing. This means that transportation agencies may not need to fully centralize data to benefit from other states' collaboration. Instead, federated learning can provide a practical and privacy-preserving pathway for improving infrastructure asset management. The framework can be expanded to other infrastructure assets and additional transportation agencies. Overall, this work shows that AI can help agencies prioritize inspection resources, support proactive maintenance, and make better data-driven decisions while respecting data ownership and privacy. Thank you very much for your attention to this presentation. I would like to acknowledge Dr. Abbas Rashidi, the University of Utah Department of Civil and Environmental Engineering, the Utah Department of Transportation, and the City IPS for supporting this research. This work is a part of the report titled Data-Driven Inspection Planning for Utah Culverts Using Federated Learning. You can scan the QR code here to access the report. I appreciate your time and I welcome any questions or feedback about this project. Thank you.
Thank you. And I did throw the link to the research page on the CTIPS website in the chat. So if anybody wants to link to that report, you can certainly link to it there. I have a couple of questions. So you mentioned, I think it was 242 culverts were in the inventory, and there was nearly 47,000 or 47,000 plus, somewhere around that range. Was where did you get that data? So 242, is that what Utah DOT had in their inventory system? And then how did you find the additional, several thousand that were added to the system?
Yeah, that's a great question. So 272 is a complete data set, which means all the features included. And when they inspected the culvert, they recorded the condition, all the features of the culvert. But the more than 47,000 is that the location of the culvert, which is not very accurate, and it's based on the third party data collection that is done every 2 years in Utah Department of Transportation. So they know that there is a culvert at that location probably, but they don't know the condition of the culvert exactly because the third party that collect this data will not inspect them. They only says that there is a culvert in that location, and to do that they use images that collected in the roads, and there's a sign that shows there's a culvert in that location. That's the only thing.
Okay. So did the results of this survey or this research project then, did that give them more data on some of those unknown culverts? Did that give them, I guess, more information for that asset?
Uh, we can guess predict the condition of the culverts. We cannot predict the location the features of the culvert. So if they have the features and they know the location, probably we can help them to predict what is the condition of the culverts right now. For
Okay.
example, they guess the age of the culvert is 50 right now. Can you predict the condition of culvert for us? And we say yes. Based on these machine learning model, we can predict it for you.
Okay. Okay. And then I guess my next question I had for you, and it kind of maybe ties in hand with that. How long did it take you to collect the data on those culverts?
Uh, the inspecting do you mean the Utah's culvert or
Yeah.
all the?
Yes.
So for inspection, they have to go to the field, and this process is very time consuming usually. And I have experience working with the asset management team of the UDOT, and based on the discussion that I have with them, usually they can go to the location of the culverts and inspect them uh, every month near 20 culverts, maybe.
Okay. And
And
then
these 272 culverts that we had the information was from another UDOT project that
okay.
done by Utah State. So we had this information from another project.
Okay. So then my last question I have for now anyway, unless somebody else asks ones that makes me think of another one, is UDOT using this information now as part of their making matrix when it comes to obviously culvert replacement, enhancements, rehabilitation, et cetera? Are they using that for their projects now?
Yeah, there's a discussion between the champion of the project that is in the asset management team and the field offices of the UDOs, so they can start collecting data and inspecting the culverts and also using these prediction algorithm for prioritizing the inspection. There's a discussion and they are creating a schedule on how we can implement this in UDOT.
Excellent. Okay. All right. What questions do you guys have for Purya?
Uh, Chris, I have one.
Hi, Chris.
So you said you could use this, Puria. Thank you for the presentation for bridges. What information would you need to extend these two bridges?
Uh, It depends on exactly the bridges information that we have. Usually, most of them are similar, so we can use. But we have to. I think for bridges we have to different between the deck and also the other parts of it. So, but for example, for the deck, we can use all of these informations, also add more data. And I know that there's a website for bridges that include all the inventory of this state duties. And it depends on what bridge, the condition of bridge is depends on what features. That's the only thing. If we need more features, we had to add this. But the whole process is the same for bridges and culverts.
So Priya, to extend this one more question, how many bridges would you need for a certain type?
If you want to use similar, at least 10,000.
10,000. Okay, thank you.
And so just one more comment. So as Puriya mentioned, so because among all federal agencies like DOTs, so data security, cyber security is becoming more and more important, right? And it's not just for culverts, but for more kind of sensitive infrastructure like bridges. So that's a kind of something that prevents openly sharing basically raw data. So that's the main purpose of the study.
Thank you, Abbas. I think that's very important.
Yeah.
Agreed. Thank you. Excellent. What other questions do you have? Okay, well, not hearing any additional questions. Thank you again, Portia, for taking the time to present to us. We certainly appreciate you sharing your research findings. Very valuable, I see here, as we move forward, and hopefully some states have some good takeaways from this to hopefully implement that. UDOT, hopefully they share that in some of their best practices as they move forward to some of their bigger meetings and things of that nature as well. Thank you, everyone, for joining us and being present in the moment. We appreciate your time and your attention for today's session, and we hope that you found today's session valuable and are walking away with some new knowledge. Be sure to bookmark translearning.org and check back for upcoming presentations and resources. Again, there will be a recording of today's event. It will be posted on that CTIPS website and also on the CTIPS YouTube page. With that, have a fantastic rest of your week. Stay safe, and don't forget to be awesome. Thanks, everyone.